All right. So the FRQs, right? You're gonna have this is half of your test. You normally you'll have 6 questions, right, for the FRQs, and you're given them all at one time. And the idea is that you want to kind of pace yourself. I would say for the first 5 questions, 1 through 5, uh, 10 to 12 minutes per question. This is what they recommend, right? And then for the 6th question, question number 6 is always like an investigative task. There's always like multiple parts to that one, that is kind of weighted a little bit heavier, and this one is worth like 25% of the score, right? For just the FRQs, yeah. So it's weighted a good chunk. So it's about 25% of section 2, right? And questions 1 through 3 are usually questions that you see in the very beginning, right? They focus on like specific skills. Like you're gonna see stuff on collecting data. Maybe you write out an experiment in detail, right? Like how you would collect simple random sample. How would you go about explaining an experiment? You talk about like sampling methods. Um, but in this also you can interpreting stuff, right? Interpreting graphs. So can you describe, say, scatter plot? Can you describe a histogram, dot plot, box plot, right? This is where you do like the compare and contrast. It's approximately normal. There's no outliers. This is where you go through that process of describing things, right? So that's a lot of like questions 1 through 3. You also do um, like regression lines are in this topic. And we'll talk about today with the regression line, like how do you describe a regression line appropriately, correctly. Um, you might get, uh, you'll definitely see something here in this section, right? Like you'll talk about normal calculation, like a z-score, interpreting it, calculating the z-score, right? So normal distributions. So you're dealing with z and say, yeah. So maybe a probability question in this topic, right? Are the things that you can kind of expect. But 1 through 3 is like on the earlier side of the school year, right? When you're just starting the course and you're describing a histogram, you're describing scatter plots, you're interpreting values, you're explaining things a lot, right? Questions 4 and 5 are like the actual test, like the significance tests or a confidence interval, right? So this is like the bigger stuff that we've been focusing on lately. Confidence interval, significance test, right? This is where you like interpret the p-value. And you write the state, plan, do, and conclude, like the whole process, right? Where you want to be able to explain what things mean. You can also see stuff like chi-square, proportions, all that kind of stuff, right? All the different tests that we spoke about, they're all fair game. But like your goal for this test is to aim for like a 50%. And it depends on your strengths, right? Like, are you better at FRQs? Are you better at multiple choice or a little bit of both? But if you can get a 50 on the test, you'll get credit for college, right? In total. So you can get a lot of your points on the FRQ or a lot of your points from the other one or like half and half, right? Like if you can do, I would try to not leave an FRQ blank because they'll give you little points here and there, right? So even if you don't know how to do something, if you can interpret and you can say, hey, if I knew how to do this piece, I would do this, this, and this for this other parts, right? So maybe you only know the conditions, or maybe you only know how to interpret a confidence interval, but you forgot how to calculate it, right? So you can say, assuming that a confidence interval is between this range and this range, this is how I would go about interpreting it. And they'll give you points for hypothetically interpreting a value. Or you can find the p-value because you forgot how to use the table. And you're like, oh, well, if the p-value was less than 0.05, I would reject the null hypothesis, right? If the p-value was higher, I would fail to reject it. And you can still write an entire FRQ with like zero math and get the majority of the points for it because you know how to speak the language, right? You know how to communicate it. You're just missing little pieces here and there. So if you don't know how to do something, can you write a null hypothesis, an alternative hypothesis? Could you check some conditions that you remember, right? Can you state what type of tests you would do? And then can you hypothetically even create a p-value? Like all of that stuff, right? FRQs, you can get a lot of your points through just the wording and your explanations of stuff. Yeah. As long as you're not contradicting yourself with what you're saying, you're pretty safe, right? And then question 6, they usually give you something that you've never seen before. Something that we can't prepare, like bootstrap method, something with like a really weird sampling technique that you're like, what is this about? So if you spend a good 10 to 12 minutes for these 5 questions, that's like an hour tops. And then they recommend 30 minutes for this last one so that you can just, okay, let me pace myself here. Let me think about this a little bit, right? What does this mean? And then there are probably going to be some like data, like histogram or a big table or a lot of graphs. And the goal is to be able to sort of put things that you know together to create a conclusion about something that you don't even know, right? So question 6 is where you use your statistical mindset to conclude something with new data or a new technique. The goal is not to know the technique. The goal is just, can you interpret numbers on the fly, right? Can you read X and Y axes? Can you interpret like a box plot or a dot or histograms and just kind of make sense of big picture, right? I recommend taking deep breaths between questions and just pausing so you can recenter yourself, right? And even if you don't, right, can you bank yourself on the other stuff, right? The multiple choices that where you do the calculations or you interpret parts of the thing, right? Like maybe you're already given the z-score and the p-value, and you just like find the multiple choice that best matches the confidence interval or best matches that kind of stuff. Does that help a little bit? Explaining and understanding the overall concept of things. So usually you'll have something with regression. It'll be one of these, right? Or something to do with like question 6, right? So I want to go over regression so that we have an overall understanding of what a regression is, scatter plots, and make sense of it all. See? Okay. But yeah, you're not going for like a perfect score, right? Usually it's like a 50 is definitely like a 3-ish or 4, right? It's normally distributed, like, because there's so much variability in FRQs and free responses and stuff. There's like, so the test is normally distributed, right? So you'll see stuff like you've spoken about, right? A good chunk will be in the middle, and you'll get your 3s, your 4s, and your 5s are going to be like way at the top, right? But even if you don't get a perfect score, you can still get like a 5, right? AP exams in general are standardized, so they look at how the population performs and like, all right, we're going to give a good chunk of the people here in the middle a 2 or a 3, and then we slowly start to limit them out. But 2 is like the most common score that people get, right? So if you feel decent with like half of the material, you're gonna be okay. You're gonna be okay. You just gotta like pause, write as much as you know, even when you don't know stuff. Can you talk statistically, right? Using the language that you've learned. So let's talk about linear regression. So a linear regression, right? I'm gonna start from scratch a little bit. For chi-square, when we had two categories, right? And we're trying to figure out whether or not these two categories were associated or not, or they're independent of each other, right? The relationship between two categories, we had a chi-square test for independence. Or association, whichever word you prefer, right? Are these associated? And we spoke about this last time with a two-way table, right? And we were looking at category 1 versus category 2. And we were saying, hey, are these two associated or independent of each other, right? So when you're comparing or you're trying to identify the relationship between two categories, we go with chi-square test of independence. Well, when you're looking at the relationship between two quantitative variables, right? The relationship, let's say that you're dealing with, is there a relationship between the height of someone and how much ice cream they eat, right? Or their body weight, or like any two quantitative variables that you're comparing, right? Numerical values here. So like, let's say, since we're in basketball season right now with the Spurs and all, let's say, is there an association or a relationship between the height of a basketball player and how many points they score per game, right? Now, you would kind of want to look at it like as an X and Y axis, your independent variable versus your dependent. Although you normally don't, it doesn't really matter how you look at it, right? But you do want to have like a general idea of like what depends on what. In this scenario with basketball points and height, which one do you think depends on which one? How? Yeah, the number of points depends on height because we're trying to see if there's a relationship, right? Is the taller you are, the more points you make, or the smaller you are, the more you can like get in there for layups, or like how does that work, right? So you can look like at the height of a basketball player and the number of points. And these are both numerical, right? You can measure both of them. And let's say that somebody, like you're looking at someone's height, and you have a dot. This is how many points that person made. You will look at the height of a person, and then how many points that they make. And then as you start plotting and you're taking different samples, you're trying to figure out, is there a relationship between these? Positive or negative? Is there a relationship between these two values? And what do you remember from Algebra 1 that describes the relationship between dot plots or scatter plots? Okay, yeah, that gets us there, right? So if there is a relationship between these, then you're going to see some sort of trend, some sort of linear trend, right? That tells you that you can use to predict the number of points based on the height, if there is one. If there isn't one, then you're going to see a scatter plot that looks like this. Right? Sorry. And when it's all scattered, you're like, man, it's really hard to see if there's any relationship because one does not help me predict the other, right? Knowing this variable, the height, does not help me predict the other variable, right? So what you're looking for is you're trying to figure out, is there a linear relationship, which is why we have the statistical test that we're dealing with here. Correct. Yeah, so there's different layers to this, right? You first want to start by identifying. So here we can have two different types of tests that we can do when you're dealing with a scatter plot. One, you want to be able to describe a scatter plot. right? And I can go over that here in a little bit, like the different things that you would describe when you're doing one. Just like when you describe a histogram, you wanted to look at the shape, the center, the spread, the outliers, right? All that kind of stuff. Scatter plots have their own way of describing them, and we'll go over that in a minute. But yes, our goal here is to, can we find some sort of linear relationship between the two to help us predict, right? And we use this, it's kind of like y equals mx plus b from algebra 1, but in statistics we switch the order. We put the constant first, like the y-intercept first, and then the slope with the x value. And we use the hat because this y hat represents, this is our predicted value. Right? We're using a line to predict one and the other. And you're right. You're absolutely right. Just because there looks like there's a relationship doesn't mean that one causes the other. And we're not really using this part of the test. A linear regression will not help us do that. It helps us predict on average, right, what can happen, as opposed to this thing depends on this one for sure, right? Like there is a relationship between heat, how hot it is in the well, let me trace back a little bit. There's a relationship. I can do a scatter plot between the number of ice cream cones sold and the number of crimes, right? The hotter it is, the more ice cream you sell. But also the hotter it is, then the more crimes there is. So yeah, you can have confounding variables that are in the background, like lurking variables that say, hey, this doesn't mean that this causes this one, right? Like ice cream sales does not cause more crime in the city. There's something else in the background that's affecting it. So it's good to know how to talk about that. But when you're going to be asked about these questions, is you're going to be given something to see whether or not you can see if you can find a linear relationship between the two to predict the other. And there's a lot of things that go into that type of test, not just, oh, it looks like a line, so yeah, we're good, right? There's a lot of aspects to it, several conditions that we want to measure and check. But this is the idea, right? Can we take a sample, like basically the entire course, based on a sample, and if it meets the conditions of that sample, right, are we able to use that sample to predict the true value or the true slope for the population? Because slope is what measures that relationship, right? If it's a positive slope, it measures a positive relationship. If it's a negative slope, it measures a negative relationship between the two variables. The steeper the line, the strong, right? Or the closer the dots are going to be, the stronger the relationship, as opposed to the weaker because they're more spread out. And there's a lot of components into that. But when we're doing a significance test, we're doing a test for slope. And we use beta for slope, for the parameter of slope. Right? This slope, this lowercase m, or I'm going to use the equations that you're going to be seeing. This slope right here is based on your sample. And this is the sample y-intercept, right? The constant. And we're going to use the sample to make inference on the true population, right? All of these significance tests are like that. You're based on this sample, can I make a confidence interval or find or do a significance test to make a conclusion about the true population? Yeah. Now in there, I put the conditions for a regression here on the side that you can see. But here's a general scenario, right? We have two things that we can do for linear regressions: significance test or a confidence interval. And it's for slope because slope tells me the relationship between the two, right? If it's positive, it's negative, that kind of stuff. We're not going to do a significance test for the y-intercept because that's just a starting point, right? That's a starting value. So here we have a scenario, like let's say that we have, consider the population of all of the eruptions of the Old Faithful geyser in a given year, right? For each eruption, given that x is the duration in minutes and y is the interval of time until the next eruption, suppose that we have all these conditions met, and we can read these conditions here in a second. The population regression line is this right here. It's mu y equals 34 plus 10.4x. Now we'll talk about the interpretation of what these numbers mean here in a minute. But if you prefer to write it the other way around, where you write it as y equals mx plus b, then this one here is your slope, right? The 10.4 represents your slope, your rise over run, and then this is your y-intercept, or when x equals 0, right? This is the starting point. Now, for conditions, we want to know, is the data, does it look linear? Does it look like we're following a linear relationship? Or does it look like this? If the data looks like this from our sample, like, there's really no purpose of moving forward, right? But here we kind of see that there's like a linear relationship. Are the observations independent of each other? If we're looking at basketball players and the number of points, yes, the observations are independent, right, from each other. We're looking for whether or not it follows a normal distribution. Now, what does that mean, a normal distribution? Well, when you're looking at your data, technically here, if I look at it at an angle, for every interval or every value here, we're really trying to see whether or not it's normally distributed about that line we're going to be using. Right? Is our data normally distributed? Sorry, I keep not looking at it. Meaning, like, how is it spread around, right? Is it approximately normally distributed along the way? And I'll show you other graphs that you can also use to determine whether it's normal or not normal distributed. We want to look for standard deviation. Does it look like the standard deviation is about the same across? The spread looks about the same, right, as you're going through it. And then the data comes from a well designed random experiment, right? We're collecting data randomly. So now from here, right, as you look at this equation, you can do different things with that equation. From this equation, you can answer the question like, find the average amount of time until the next eruption, given that the eruptions lasted 2 minutes. Well, this line here helps us predict that. As long as we know what the input is and which variable is the output, I can use 2 minutes for whatever I'm looking for, right? So that comes from here, right? Let x be the duration in minutes and let y be the interval of time. So the eruption lasted 2 minutes. That's my x value. And I literally use this formula, 34 plus 10.4 times 2. And then I can do some math, right? This is going to be 20.8 plus 34, that's 54.8 ish, right? So we can use this right here to make a prediction of like the average amount of time spent in the next eruption using this right here. Right? You collect a lot of data and you could go to the line of best fit. I don't know if we remember some of these words from Algebra 1, right? This is like the line of best fit for the data. You can go to 2 and go to the line to identify that number, right? That's going to be somewhere here, which is 54.8, somewhere there between 50 and 60. Or you can use the equation to find the exact value, right? But this is the average amount of time, right, for the next eruption, given that the last one lasted 2 minutes. You can also build a confidence interval around this thing right here. If you know the mean, you can build a confidence interval around it to tell me, hey, between around how much, right? This is just one sample statistic, but we can build a confidence interval with like a plus or a minus on both sides to determine an interval, right? Why would we want to use an interval versus a specific number?
So it's not like what you're thinking has to be spot on. That's like
Yeah, you have a little bit more wiggle room to identify around how much time, right, does a confidence interval provide. And you have like the plus side on the top and then the minus on the bottom. Using the empirical rule, 95% confidence, what does that look like, right? As a quick recap. How many standard deviations is it from the mean? 2, right? Now, 1.96, I believe, is the exact value, but if we're using the empirical rule, the general formula for a confidence interval is you use the statistic, you use the critical value, right, times the standard deviation of the statistic. That's your general confidence interval, right? The statistic that we found was 54.8 for that calculation that we did. The critical value, we're going to use 2 using the empirical rule. And then the standard deviation is given to us as 6 here at the top. So you would have 54.8 plus or minus 12. And if we do a little bit of math, right, what's my interval going to be between 66.8 and 41.2? If I'm subtracting 12 here, it's 42.8. There you go. I should have just shown my work, right? So how would you interpret this confidence interval as a recap, right? If it's a 95% confidence interval to predict the amount of time the next eruption will occur, given the previous one lasted 2 minutes. We're 95% confident, yeah? Absolutely, right? We're trying to predict the true value here using a sample. So we are 95% confident that the true amount of time it will take for the next eruption, given that the previous one was 2 minutes, will be between 42.8 minutes and 66.8 minutes. And we used this data to create that kind of interval, right? That kind of prediction. Or you can say, if we take many samples, 95% of those samples will fall within this range as an interpretation as well. But we're trying to interpret the true value, right? And I know I don't have to sit there at 30 minutes checking my clock. I can just wait between these two ranges, knowing that I'm 95% confident it will land within this time frame, right? But the main component here that I want to express, right, or focus on is that linear regressions help you determine or reflect the relationship between two quantitative or numerical variables. When you have one numerical variable, we're not finding the relationship. We're doing like a Z table or T table, right? We're taking a sample to make a prediction. Well, here your prediction will be about the slope, right? We're going to be making predictions on slope, the true slope between these two variables. That's really what we're focusing on when we're talking about a significance test here, right? We're making an inference on the true slope or the true relationship between these two variables, if there is one. What do you think will be your null hypothesis? That there's no relationship. So the slope should be what? 0. There's no relationship will be my null hypothesis. And then the alternative will be based on whatever they're saying here, right? Is it a positive one? Is it greater than? Is it less than? Like what side of the table am I looking at? That kind of stuff. But now we're going a little bit more into that kind of stuff. How do we feel? Okay.
So what does it mean by
that was when we were looking at like this right here. So across the board, do we have about the same variability, right? And we normally don't look at this plot. You're going to be given different kinds of plots, and I can see if I have, yeah, here I have a few. It's probably hard to see because of my lines, but here you're given like a line. There's different kinds of plots, right? So when you're checking the conditions, right, here's a scatter plot. You want to make sure that there's, first of all, like a linear relationship of some sort. Does it look linear? Here, it looks like there's a negative linear association between these two variables, right? Because it's pointing downward, and there is a bit of a line going through that, right? Versus in the previous example that I showed y'all, there was nothing, right? Usually we use R as a way to measure the correlation between two variables, right? Did you guys talk about that at all?
Yes, we did talk about that.
R values and stuff,
That honor cost.
and how to predict it, right? Like if you can trace around all the points in your data set, the closer that that shape looks like a 0, the lower the R value is going to be. And if you have points that are more associated when you trace them, if they look more like a 1, the closer they will be for R equals 1, which is the stronger correlation between the two. Or if it's pointing the other direction, maybe it's like a negative 1, right? But depending on how round it is, the more it looks like 0, then the lower the R value is going to be. And yes, R value alone doesn't really tell us much, but it can get us started to describe the kind of linear relationship that we see. Another thing that you would look at would be like the residual. Now, a residual happens when you take the actual value minus the predicted. And what do we mean by actual value? It's like, well, each observed minus expected. Yeah, there's different ways of saying that, right? So, and that's where you, let's see, you look at your residuals. What language did y'all use? Observed minus expected? Okay. I mean, yeah, that's usually what happens. You use what was the other one over there? Experimental, like the actual data point, right? Minus the expected or predicted, depending on what word you want to use, right? Observed minus predicted or expected. Observed being the actual point. And then the line, anything on the line is my prediction, right? So I want to measure the distance between these 2 points. That's really what's happening here, right? The actual data set, how far is it from the line? That distance is a residual. So when you're subtracting these, right, and I can look up the formula real fast just to make sure that the language that you use, residual, is on point. Yeah, so actual minus predicted is the language that they use in your test. Actual value minus predicted. Right? So y minus y hat. The line being your prediction, right? And then wherever the dot lands becomes your y value, your actual value that you measured. The data set itself, right? Now, if I subtract these and I get a positive residual, what does that tell you about the data point? Is it higher or lower than predicted? So this is the actual data set, right? That would be up here, right? A positive residual would put you above the expected line, right? A negative residual would put you below the predicted value. And that could be a question that you might see like on a multiple choice, like how would you interpret this residual, right? Oh, this is above, so I'm expecting this number, but this person scored more points than I predicted based on my line. Okay? Now, if you subtract every data point from the predicted, you can create a residual plot. So a plot of just residuals, and it will say on the side residual. I don't know if you can read it on you. We got new printers today. But this is like your residual plot, right? And we're looking for a residual plot that has no apparent patterns here. That's what we're going for. Now this one does have a pattern. It's got a curve. So this tells me that it does not meet that kind of condition, right? There's something underneath that is masking what this looks like to be linear. We're looking for something just scattered, about the same number of points on top, same number of points at the bottom, because then you have about the same amount, right? This is where you go about interpreting the standard deviation. Equal standard deviation, if you look closer to the bottom, we have a few more residual plots. Which of the two looks like they have the same kind of residuals? This being 0 in the middle. These are both residual plots.
The first one.
The first one fits better. It's evenly spread out. There's no like apparent pattern. This one has a bit of a pattern.
The side was
Yeah. And we're looking for something that's evenly spread out, right? When things are evenly spread out on top and in the bottom, that's the equal standard deviation component, the condition that we're talking about. It's evenly spread out and there's no pattern, so I can use that. And you can read some more of this. Like I wrote like the exact wording that you can like, the language that you can use. For normality, you can also look at a box plot or a histogram or some sort of plot to show that the residuals are normally distributed. So you would see a histogram with like residuals in the bottom. And then this is like a frequency table. And you just want to make sure that it's not obviously skewed. Nothing will ever be normal, right? So it's just going to be approximately normal. Unless it's like clearly skewed, then it does not pass the normality test. Why do we want it to pass the normality test? Well, we're going to make a confidence interval, and we're going to use confidence intervals and a t-test to be able to make our predictions. So we want to make sure that our data is normally distributed in order for us to make those conclusions. Otherwise, we can't use a t-test for this, right? Is that okay? Am I going too fast, or are we okay?
so this really is 5% confidence.
Yeah, I mean, if it doesn't pass the normality test, it's really hard to do anything. So in an FRQ question, they're not going to give you something that doesn't meet the conditions. Unless the question is just, does it meet the conditions? But usually the question is so you can do more with it, right? Like find the line, make your prediction, like go beyond it. Very rarely will you not get a scenario that meets the conditions, right? And if it doesn't meet the conditions, what can I check for the sample size? When I look at the frequency table, the frequency on the side, what can I check for frequency if it looks skewed? If it's, let's say that they do give you this and it is skewed, how can I use the frequency table, these bar graphs, to determine whether or not I can proceed? What sample size do we want?
You want to
More than 30. So look at the bars. Maybe this bar is 15 and this one has like 5 plus 5. And you're like, you know what? Yeah, this is clearly the sample size of more than 30. So we can bypass that condition, right? Using the central limit theorem and blah, 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 blah. Now these are just conditions. You can go into that. Like this is a lot. You're not going to write all of this. This is just the details so that you can like make sense of it. Yeah. What we want to do is this, right? Can we build a confidence interval? Can we do a significance test and like interpret the important values? Normally we would be probably done closer to now, but this is a new topic for y'all, right? Now here, this problem is talking about, does the seat location matter, right? Is there a relationship between the scores in the test or in the grade level versus where you sit, right? Based on the rows and where you sit. That's really what this one is about. Now, for this example, I want to show you a confidence interval, right? We want to look at all of this information. This is like an output table, and I'll show you how to read all of this. So we're going to look at the coefficient. That deals with this component, a plus bx. These are the coefficients, right? Which one of the two is the y-intercept? Letter A is our y-intercept. Which coefficient here corresponds with the y-intercept? Constant. When it says constant, this will always be your y-intercept. Right here. I can write it as 85.706. Rho is the thing that we're trying to associate right here. That's a slope. Right? So our slope here would be negative 1.1171x. And there's ways of interpreting this, right? How would you interpret the y-intercept? If x is equal to 0, right? Meaning like if you're sitting at the very front, like 0 row level, you can predict the person's score is 85.706. right? The slope, this is your rise over run. This could be written over 1. Well, what is the rise in this scenario? Score is your rise. The run is your rows. So how would I interpret that slope with score being on top and the row that you're sitting on being in the bottom? Since it's negative, what does that tell you? As I increase, for every one row that I sit further back, what's going to happen to the score of a person? It's going to decrease by 1.1171, right? That's like your interpretation of that slope. For every row that I go back, we will see a decrease in score by -1, or a decrease of 1.1171. Yeah. Now, we're looking at the coefficients. Here in a little bit, this is the standard error of these coefficients. There's some formulas that you're given that would help you also calculate stuff when you're dividing standard deviations and stuff. This is the t-statistic. And this is the p-value of each statistic. Now, we're interested in doing a test statistic for the slope. So we're going to be using that p-value to make a conclusion about the test statistic that we found for that slope of our sample. Yeah? I know this is a lot. So here, the first question would be something like, identify the standard error of the slope, right? From the computer output, interpret this value in context. How would we go about interpreting, say, the standard error? Where are we at? Standard error coefficient of the slope. So we're looking at this component, right? Let me see. I have some scenarios here. What did that tell me here in terms of like my distribution? This is the standard deviation, right? For slope, that's how far the slope is being spread out. This is my standard deviation of the row of my equation. The line looks like this. I don't know if you can see it on yours. Mine is pretty faint, but it's right here. Right? That's the variability about the line, about the slope. The variability of the slope. Can we calculate a 95% confidence interval for the true slope? Right? 95% confidence, I would also use 2 for my empirical rule. My statistic, what is the statistic for the slope? Negative 1.1171, right? That's my statistic. It's the coefficient I'm working with. The standard error of that coefficient is 0.9472. And then I can build a confidence interval around this, right? From here to what value am I going to be able to see that? That's really what we're doing, right? We're building a confidence interval around that. And we kind of did an example earlier, right, with that. That's really what we're saying. It'll help us identify between what range, right? 95% confident between what range is the true slope between these two relationships. What do we get here? Let's do some math real fast because this will help us answer the question so you can kind of get an idea of things. 0.9472 times 2. We're doing negative 1.1171 plus or minus 1.8944. So plus 1.8944. On the plus side, we would have 0.7773. And on the minus side, when you subtract, it's negative 3.0115. Yeah? What does this tell you? We're 95% confident that the true slope or relationship between these two variables is between negative 3.015 and 0.773. Does that help? Right? Now, we were trying to see whether or not there's a relationship. The null hypothesis would have been that the slope is 0. Right? There's no relationship. Since the slope is within our confidence interval, what can you conclude? Do we have enough to reject that there's no relationship? Yeah, it's part of the interval. Had our interval been way far away from 0, we're like, hey, there's a relationship because our true slope is between, let's say, 5 and 10. And it's pretty far away from 0. So there is a relationship. Here we don't have convincing evidence since 0 is here. And that's how I would interpret it, right? Since the true slope would be between this range and 0 is within that interval, we do not have convincing evidence, right, that seat location is related to scores. And if you look at the picture, I mean, it's kind of scattered everywhere, right? And the line is very minimal, like it's almost flat, right? The slope is almost like 0, right? So, are we okay with the conclusion here? Do we have convincing evidence? No. And I would say that by talking about how 0 is inside of the interval. If it were outside the interval, let's say that this is 0 and we found numbers between 0.773 and 2.91, right? In this scenario, we would have convincing evidence. I would say I'm 95% confident that there is a relationship between the seat location affecting scores because the slope is not within my interval. So we use the interval to make a conclusion, right? We determine whether or not it's in the null hypothesis. How does this affect our null hypothesis? You could also do a test statistic to make the same kind of conclusion, right? You can use a confidence interval or a t-statistic. The t-statistic tells you the probability of something happening, the p-value. Yeah? Are we okay with this interpretation? This would be a no, and this would have been a yes. Kind of on the quicker side of things. Let's say that we had a test statistic instead. How would we do this kind of question differently for a test statistic? Well, you would still have your same null hypothesis and alternative hypothesis, right? B is equal to 0. Here, usually B is just not equal to 0, right? It's a relationship or not relationship. Or unless they're saying is, like in this question, actually it wouldn't be not equal to 0 because sitting closer causes a higher achievement, right? What are we looking for here in terms of the relationship? What kind of relationship would we want to find evidence for? Well, what would the slope look like based on the row? This is row 1, 2, 3, 4, 5, 6. It would be downward, right? We're hoping for something like with a negative slope. Thinking that the further away you sit, the lower your scores, and the closer you sit, the higher the scores, right? That's like the thinking process. So I would say that the slope is less than 0. It's what we're trying to find evidence for. A one-sided test. And it all comes down to like the scenario, right? What would like it look like? What would make sense? Sometimes they tell you, sometimes they don't, and you kind of just make sense of things, right? Now, we would go through this whole process, the conditions. You would talk about like, this appears to have a negative linear association, right? Because it's kind of going downward. There's no other graphs, so you can assume normality. You can do a lot of these different things through assumptions. And then you would do the actual math. Well, we're looking for a test statistic, and for the t-test, we have a critical value. Since we're doing less than 0, we're looking for a t critical value. And we want to know, is our critical value in the rejection region? Is my test statistic in my rejection region? And the thing about this one is you don't have to do a lot of math because you're given all this information up here. Right? If you did have to do the math, they would tell you what to use, like formulas and things like that. But you normally don't. What they're interested in is in your understanding of the math, right? Of what it means. Now, this is your t statistic. We're trying to interpret what? Slope, which is this one. What is the t statistic here for my sample? Negative 1.18. I want to know if that negative 1.18 is significant or not. Well, do we have the sample size? Do we have the degrees of freedom? Are we able to do that? No, not in this problem. If we had the sample size, you would do degrees of freedom minus 2 because you're dealing with 2 variables. And then you would go to your table, your t table, and you do degrees of freedom minus 2 and calculate the t critical value, right? But we don't know that information. We can't use the t table. We can't use this and say, so what we do is we are given the p-value though. We're given the p-value of this statistic. Now this is a two-sided value. This is two-sided probability. What do we do with that probability since it's only a one-sided test? Divided by 2. The p-value divided by 2. So since the p-value of this statistic is 2.248, when you divide it by 2, the p-value for this test is 0.124. Sorry. You can tell that I don't teach like this on the projector because I don't even know where I'm at. How do I interpret this p-value? Is the p-value less than 0.05? No. So we can't reject, right, the null hypothesis. Since p-value given is not less than 0.05, we fail to reject the null hypothesis that beta is equal to 0, right? That the true slope is equal to 0. We don't have convincing evidence. To support what? To support a relationship between scores and where you're sitting at. We don't have it. And we got the same result, right? When we were doing our conclusion for interval. 0 was in our interval and we had the same conclusion as we did with our test statistic. Except that in test statistic, we're using p-values and t critical values as opposed to an interval that creates that. Now in your formula chart, I know they're going to give you how do you find some of this information. Like if you're not given this, standard error of the coefficient so that you can calculate your plus or minus, right? You do have it in your formula chart, so feel free to check in your stuff that you're given. You're given formulas to find the standard error of slope. There's like a whole section on that. And then you start to divide things, and like there's different things you can do to do that. Does that help? So if it's in the interval, We fail to reject the null because it's one of the things that is possible, right? If the probability is not smaller than 0.05, we also fail to reject it. And then the only, yeah? Yes. Yes. Now, the only thing that we haven't interpreted really, we interpreted slope, the y-intercept is the r-square value. I do want to talk about that really quick, right? The r-square value here is 4.7%, which is going to tell you a lot. R squared comes from R, the correlation, right? When you square the actual correlation, you get the R square value, right? So if I wanted to find the correlation, I can take the square root of this number, right? And I can find the correlation between the two of 4.7 or 0.047 because it's a decimal, right? A percent?
No, 0.0.
0.047, right? 4.7% would be 0.04 as a number, right? So when you square root 0.047, you get an R value of 0.216, which is pretty low, right? It's positive, but it's a little low. This will tell us maybe our conditions when we're looking at correlation between the two, right? It's a weak relationship between the two because it's close to 0 than it is closer to 1. Now, how do we interpret the R square value? R square value tells you the amount of variability that can be accounted for by this line that we created. What was it? By 85.706 minus 1.1171x. How much of the variability that can be accounted for in the y direction as x changes? So this line, basically, in other words, right? This line has variability. It varies, right? This is how far things are. Another way to think about R squared is it helps you with your accuracy. If I use this line to predict something, this is kind of how accurate I'm going to be. 4.7% of the time, I'm going to have a good prediction. Is that a good prediction? 4.7%? It's terrible. 4% of the values in my data can be accounted for by this line. Now, the closer the points are to the line, the better your predictions are going to become, which increases your R square value. You're going to see a way higher percent. This value is what we really help to determine that relationship. R is just an association, a correlation. Is it positive? Is it negative? Is it strong? Is it weak? Right? Is it pointing up? Is it pointing down? But R squared tells me how good of a line this is going to become for my data set. And the higher the R squared value, the more that variability, this variability, will be accounted for in your prediction. That's really what R squared tells you, and it's a really powerful tool. So you can see something like that in an FRQ, or you can see something like that in multiple choice, right? Can you interpret the R squared value? And it's the amount of variability, the spread, right? The spread about the line. The amount of variability that can be explained or accounted for as this and this change. It depends on the wording here, right? So the amount of variability that can be accounted for or explained by with the equation, predicted. Yeah, but it could also be misinterpreted with we're in essence saying the same thing, right? Like, .7% of the data can be accurately predicted by this line if we run the experiment many, many times, because this is just one sample, right? We're trying to infer on the true population. So for the true population, assuming that this line is the true values, the true information is on the line, and everything else is a variability, it helps to say how much of the variability can be accounted for with this line, right? And then you can add predicted as long as you're focusing on the true value, right? The true relationship, the true slope that's explained by the line. But we're really talking about the variability. How much of this spread, if I focus on this sideways, how much of this variability can be accounted for by the line? And the further spread out things are, the lower the variability. The tighter things are, right, the smaller the variability. And more can be explained.
You said that the further the layer, the lower the.
Oh, that's my bad.
Okay,
No. The further they are, the bigger the variability, right? The less the R-square value you're going to have.
Okay.
The tighter things are to the line, the higher the R-square value is going to have. I'm sorry about that. Now, you just did a 2-week thing in an hour and some change. So this technically is not everything, but if you understand the overall concept of what you're dealing with, we're dealing with 2 numerical variables and you're trying to determine the relationship between the 2, right? Each dot here is one sample. It measures a person that sits in row 4 and their score. So one dot represents an individual. That's also something that they can say, hey, how does this person, and they might circle it in the test, how does this person influence the slope? Does it positively affect it? Does it negatively affect it? Or does it not play a role? Well, when it's on the line, it doesn't affect it at all because it's on the line, right? But if it's up, is it closer up here where it's pulling the slope up? Or is it on the bottom where it's like bringing the slope downward, right? How does this outlier affect the slope? And you can kind of like think about it that route. Yeah, but you're identifying the relationship between the 2, and we can use slope, which is our value. Our t-test can come from here, the p-value can come from here, the standard deviation when you're dealing with confidence intervals can be done from here. You can do a lot, you know? So very few calculations and more how to use this table to make your conclusions. Yeah? Any questions? I know this is a ton of information. But yeah, we just kind of went through 2 weeks.
Did you say that this is the last unit?
This is the last chapter, and different teachers do it differently. Sometimes people start with this because it's closest to Algebra 1 that they remember with slope and y-intercept. Some people wait till the very end for this topic because it's Algebra 1 and this is something that you don't have to necessarily, you're not learning what slope is. You're just applying it to a statistical way of explaining it. But it's usually covered either in the very beginning or at the very end. So it makes sense that you guys didn't cover it because sometimes they're like, hey, well, let's focus on the other stuff first.
I think this did, I found it was like half the program. I think it was in like the
Okay. Well, did it help a little bit? Make some sense?
I forgot.
Yeah. Okay. You guys are doing great.